Hi, my name is Brian Caffo, and this is a lecture on multivariable regression in the Coursera class on regression. This class is co-taught by my collaborators Jeff Leake and Roger Pang. So in this class, I'm going to just go through some simulated data and just show you kind of examples of adjustment and what adjustment is accomplishing and what kinds of things can happen. And I'm going to use simulated data so that we can kind of know the truth. Okay, so I'm going to set n of 100, and then let's see. So t here. Let me get that a little bit better. Is a kind of a treatment effect. That variable looks something like this. This variable right here looks something like zeros repeated n over 2 times and then ones repeated n over 2 times. Okay? And then my x variable is just a series of uniform random variables. I don't know why I did it that way instead of just doing runif n. Here's my intercept, my slope, which I set to be 2, my tau, which is going to be my treatment effect, and then my variance. Okay, so I simulate my outcome. It's my intercept plus my regressor times my slope coefficient plus my treatment effect times the treatment effect parameter plus the epsilon. That part right there is like epsilon. So we're sort of fitting the model. Yi equals beta naught plus beta 1 xi plus beta 2 ti plus epsilon I, where ti is a 0, 1 variable. Okay, and then I'm going to plot it, my x and my y, and then I'm going to add a line where I disregard the treatment, and then I'm going to I'll tell you what these are, or I'll show you. I think this will be clear why I do this in a minute. This is the mean for the treated group, for the untreated group, right? This is the mean of the first n over 2 observations, and this is the mean of the latter n over 2 observations. And then this is the model we fit that's correct, that includes a treatment effect. And then I'm going to plot the fitted lines for the two of those. And then this plot, the first plot right here, actually, I have this type equal n right there, and that just means I didn't actually do the plot. It just created the frame, and then here I actually do the points. And I did it that way, so A, I could have different color points for the treated and the untreated group, and B, I wanted my points plotted last, so they go on top of the line. So, okay. Go through that code. It's in the Slidify notes. Okay, and it looks something like that. Okay, so this is a pretty good example of regression adjustment, or a pretty reasonable example of regression adjustment. So the true lines are parallel, so that the effect of treatment holding x constant is the same. So regardless of what x we look at, that distance is the same. So the real kind of adjusted treatment effect is that one. In this case, it makes sense to talk about a treatment effect. But if we were to disregard treatment and just so this is the effect that we get if we fit the model LM y tilde x plus t. Right, that adjusted treatment effect is that guy right there, that distance right there. But if we disregarded it, I show it right here. Here's the difference in the means if we were to have disregarded x and just done absence of covariate adjustment. And to me, those look about the same. Okay, which is good. Means that it didn't matter whether we regressed on x or not. But let's keep going. Okay, so let's discuss this first, and then we'll keep going. It's going to get harder. So some things to note about this simulation. The x variable is unrelated to group status. It's uncorrelated with group status, right? It was just a bunch of uniform numbers. So the x variable is related to y, and the intercept depends on group status, right? We had two separate lines. And then, of course, in this case, the group variable is related to y. And we have a meaningful treatment effect. The group status in y is constant depending on x. That means the two lines are parallel. Okay, and that's just reiterated in this last point right there. Okay, so now let's look at some harder cases where things are less clear. Okay, here's a much harder one. Or not harder one, but it's something that could happen. Here, I forget which group was treated and control, but if we take the difference between the treated and control, we get a massive effect, right? But then if we adjust for x, right? If we adjust for x, then there's no effect, right? There's absolutely no effect, right? Because the line for the blue guys and the line for the red guys, assuming they're parallel, and regardless of whether they're assumed to be parallel, their difference in intercept is going to be very small. Another thing to point out on this one, there's almost no overlap. There's almost no direct comparison of the treated and untreated group at a specific value of x. If you hold x constant at any value, you don't have any both red and blue dots, right? You only have blue dots or red dots, which means these groups aren't terribly comparable, right? So this this effect, which disregards x, if x is an important confounder, that has the problem of disregarding x, and it obviously gives you a tremendously different effect than if you incorporate x. But even if you incorporate x, you know, there's a problem in that the groups aren't terribly comparable. The estimate is all model; it's no data. Okay, you know, this for the blue people, because there's no data to inform it, it could go like that, and for the red people, it could go like that, whatever, and you could get whatever effect you want, even absence of any sort of meaningful treatment effect. Okay, so let's discuss this now. So the x variable in this case is highly related to group status in this case, right? Just if I told you x, you would know what group you were in. If it was a low x, you'd be in the blue group, and if you were a high x, you would be in the pink group. The variable x is related to y, but the intercept doesn't appear to depend on the group variable, of course, but we have no data to evaluate the impact of the, for example, in the pink group, we don't have any data near the intercept, so everything is dependent on the model. So the x variable remains related to y, holding group status constant. Let's see some other points. So the group variable is marginally related to y disregarding x. That just means that those marginal means are hugely different if we disregard x. Let's see. And I think I should have expanded on this point right here, that the x variable remains related to y holding group status. So that what I mean by that is if you look just at the blue group, it appears to be linear and linear and related to y. And if you look at just the pink group, it appears linear and just linearly related to y. Okay. So this model, right, under the adjustment effect would have a huge marginal effect, but no adjusted effect. And then, as I said, there just isn't any data to inform this relationship between the group and y for after adjustment. The conclusion is entirely based on the model. Okay, so that's another. So we've gone two examples, just changed things very mildly, and the code for this you can get from the Slidify thing. I'm not going to show the code every. Okay, so let's look at this example, which highlights the importance of adjustment. So look at if you were to disregard x, right? Then all these red points, just imagine if we projected them onto this axis right here, then this would be the mean that we got. And this is the red or pink mean. Actually, the color label in R is salmon. This is the blue mean. Okay? And you can see it's red bigger than blue. But what happens if we do the regression adjustment? There's a clear treatment effect, right? The two lines are parallel with a separation, right? And let me just erase that so we can see it. But now, look, so the treatment effect is that, but it has the blue higher than the red. Okay, so the regression, the treatment relationship reverses itself after the adjustment. Okay, and then by the way, I don't think I've described this earlier. This line is just what you get if you disregard group status and just fit y as a function of x. So in this case, the treatment effect completely reverses itself. So let's just go through these points. So some things to consider. The marginal association has the red group higher than the blue, but the adjusted relationship has the blue group higher than the red. In this case, group status is related to x, but we do have some overlap. There were some, if you hold x constant, there are some areas where we have a direct comparison. And that's this final point right there. Okay. Okay, so here's just another kind of example of what could happen. If we were to take the marginal associations, we get that distance right there. That's the mean of the red, that's the mean of the blue. So basically no association between treatment if we fail to adjust for x. But if we adjust for x, holding this guy constant, we get a strong association. And then obviously we get clearly the incorrect regression line if we don't account for group status. Okay, so just to summarize these points again, no marginal association between group status and y, and a strong adjusted relationship. In this case, group status is not related to x. If I told you x, you wouldn't be able to guess group status terribly well. But there's lots of direct evidence for comparing the two groups holding x fixed. So this is a good example. So you would likely want to adjust in this case. Let's look at a kind of a crazier one. So here, there is no such thing as a treatment effect. So for the red group, the line looks like that, and for the blue group, the line looks like that. So you couldn't call that the treatment effect because, like right around here, the treatment effect is 0, or right around there. So this is an example of interaction. The treatment effect depends on what particular value of x that you're at. So there's both a difference in intercepts between the two lines and a difference in slopes. So that's just an instance where you don't even have, the idea of a treatment effect doesn't make any sense. The treatment effect depends on what value of x you have. In fact, it even reverses itself. Okay, so here's another simulation. I wanted to do an example of kind of continuous adjustment. So here's my y, and here I have my x1, and x2 is the color coding of the points right here. So kind of, I think lighter meaning higher values and darker meaning lower values. Okay, so this is actually a different set of data. I'm just rerunning the simulation each time. But let's actually do the 3D plot instead of the 2D plot. And there it is in RGL. And you can see that there's this strong relationship between y and x2, and then this kind of less clear relationship between x1 and y, and that's the kind of noisy regression line that we saw from the previous page. So, but what happens if we, instead of plotting y versus x1, we plot the residual of y having taken out the effect of x2, and the residual of x1 having taken out the effect of x2? There's almost no variation left, right? So y and x are almost perfectly explained. At any rate, the point of this example was just to give you an example where, in this case, x1 was unrelated to x2, x2 was strongly related to y, but the adjusted relationship between x1 and y was largely unchanged by considering x2, which makes sense given that first point. The magnitude of the slope changes. However, the residual variability is changed dramatically by considering this other variable. So I think in summary, let me summarize these final thoughts. Modeling multivariate relationships is difficult if you want to interpret them. If you just want good prediction, then there's strategies, kind of automated strategies you could follow. But if you want to interpret these results, if you want to interpret these regression lines, the practice of adjustment can have a profound effect on your variable of interest. And so I would just encourage you to kind of play around with simulations like these to see how you can get the inclusion or exclusion of another variable to change analyses. So the discussion from these analyses deals with the impact of inclusion or exclusion of variables on associations. But an even harder problem is ascertaining whether kind of X causes Y. So that, in addition to all of these considerations, adds this secondary consideration. And so that's another problem. That's kind of a hard problem. That's the so-called domain of causal inference. But for our purposes here, we want to kind of mostly understand how and why the inclusion of variables changes the relationship between a variable of interest and the outcome in a regression model. And I think these examples show you that you can get very different answers depending on how you, depending on what variables that you include.